In a moment, we will discuss chlorine chemistry, but first, let's talk about why we treat raw water. The primary purpose of water treatment is to remove bacteria, viruses, and protozoans that make water unsafe to drink. These microscopic microbiological contaminants are too small to be seen by the naked eye, but can cause illnesses and in rare cases can be fatal, which is why we kill or inactivate them in treatment. In the U.S., the Safe Drinking Water Act requires the Environmental Protection Agency to establish maximum contaminant level goals and maximum contaminant levels for numerous contaminants, plus a list of unregulated contaminants. Health Canada has its own requirements. Chlorine is the most commonly used water disinfectant. There are several types of chlorine, including chlorine gas, sodium hypochlorite, calcium hypochlorite, and bromine chloride, which is fairly rare. Most operators are familiar with chlorine gas, a yellow-green gas stored in cylinders under pressure. It is toxic and dangerous, but has remained the standard of the industry for decades. When chlorine is added to water, it reacts to produce various compounds. Some are effective disinfectants, whereas others represent the end product of a reaction that has removed an undesirable constituent from the water. In this reaction, the chlorine combines with water to produce hypochlorous acid and hydrochloric acid. Because of the ease with which it penetrates into and kills bacteria, hypochlorous acid is the most effective form of chlorine for disinfection. However, hypochlorous acid is a weak acid, and using what we know about acids, it will further dissociate as follows. The dissociation of hypochlorous acid produces a hydrogen ion, which neutralizes alkalinity or lowers pH, and a hypochlorite ion, the second type of free available chlorine residual. Hypochlorite is a relatively poor disinfectant. Also produced in the first reaction is hydrochloric acid. It too will dissociate as follows. Hydrochloric acid is a strong acid and will go to completion. This reaction also produces a hydrogen ion, which we know neutralizes alkalinity and lowers pH. However, neither the hydrogen nor the chloride ion acts as a disinfectant. All of this happens very quickly, and we can see that maximizing the production of hypochlorous acid provides the most disinfection. The effectiveness of chlorination is based on 5 important factors: pH, temperature, contact time, concentration, and other substances in the water. We know that low pH favors the formation of hypochlorous acid, whereas high pH favors the formation of hypochlorite. As pH increases, so does the less effective free residual for hypochlorite, and a longer contact time is required to produce the same disinfection. However, both are known as free available chlorine and very effective in killing bacteria. One of the most common reactions of chlorine in raw water involves ammonia. In the presence of ammonia, monochloramine, dichloramine, and trichloramine are formed. These chloramines are called combined available chlorine. Chlorination practices frequently provide for formation of combined available chlorine, which, although a weaker disinfectant than free available chlorine, is more readily retained as disinfection throughout the water distribution system.